students, we have done many episodes in the lecture series of Introduction to HDL. I have dropped this one line and just moved on without actually proving it. Hardware doesn't run line by line, it runs all at once. I said it many lines in my previous videos. These are the big mindset shift. Next, about the VLSI pipeline, I have said when we zoomed into abstraction level three times zero proof. Today, that changes. We are cracking open actually Verilog code and showing you exactly where this all at once thing happens. And then we are going to zoom out and look at how a Verilog module is actually built. Structurally, so you know what you are looking at every time you open a V file. From here on, two topics, one lecture, concurrency and program structure. Let's go. So, real quick, let's be honest about what's been happening. I have been using that line like a cliffhanger almost. Hardware runs all at once. Cool line. Sounds deep, but if I never show you where that happens in actual syntax, it's just a vibe, not knowledge. And you can't debug a vibe when your simulation output looks wrong at 2 a.m. before a lab submission. So here is the actual plan for today. First half, concurrency, the why proven with the real code. Second half, program structure, the how, meaning how a module is actually organized, what goes where, what the pieces are called, and why. By the end of this video, you will be able to open literally any Verilog file, glance at it for 2 seconds, and immediately know what's a port, what's internal, and which part of the code are running independently of each other. Let's set up the contrast because this is a whole ball game. On the left, how C or Python actually execute line 1 runs, completely finishes, then line 2 runs, completely finishes, then line 3 runs. It's a strict queue. One instruction is in progress at a given moment, and every other instruction is just sitting there waiting for its turn. That's called sequential execution, and honestly, that's probably the only execution model you have ever known because that's how basically every programming language works. Now, look at the right side. Verilog. Block A, Block B, Block C, all three are alive, all running simultaneously right now at the same instant. None of them are queued, none of them are waiting for the block above them to finish. This is called concurrent execution. And it's not some weird Verilog specific query. It's Verilog being honest about what hardware actually is. A real circuit isn't a to-do list. It's not going step by step. Every part of a physical circuit exists and operates simultaneously the second power hits it. Verilog syntax just reflects that physical truth. Let me make this contrast with something you have probably physically touched, a breadboard. Picture one sitting in front of you right now. You have got a couple of 7400 series ICs plugged in, say a quad and gate chip and a quad or gate chip with jumper wires connecting them into some logic circuits. The moment you connect that breadboard to a power supply, here is the thing, nothing on that breadboard is waiting its turn. Every single gate on every chip is powered live and actually watching its input pins, all at the exact same moment. The instant voltage changes at any point. Input pin, any single one, that specific gate reacts instantly on its own. It doesn't check what the other chips are doing. It doesn't wait for the AND gate 3 inches away to finish its turn first. There is no return, there is no queue. Every gate is just on permanently reacting the second its input move. That right there is concurrency in physical form sitting on your desk, and here is the punch. Every always block you right and Verilog behaves exactly like one of those light gates on the breadboard. It's not simulating a queue, it's simulating a bunch of independent, always on pieces of hardware that all happen to be watching different signals. Next is the reveal. Every always block is watching all at the same time. So here is what actually looks like in code. Say you have got three separate always block in the same module. First always at the rate A comma B. This one's watching signal A and B always at the rate clock. This one's watching the clock always at the rate cell. The ones watching a select line. All three of these are sitting in your file, one after another, top to bottom like normal code. But and this is the important part, the simulator does not run them top to bottom. It's doesn't finish block 1, then move to block 2, then move to block 3. All three are always watching their own trigger signals permanently simultaneously for the entire duration of the simulation. The moment clock changes, that second block fires, completely independent of whether the first block has finished or even fired at all. There is no finishing, there is no order. They are just all live all the time, exactly like the gates on the breadboard. Program structure module. Okay, topic switch, same episode, second half. Let's talk about program structure, how a Verilog module is actually organized. Here is the cleanest way to think about this. A Verilog module is basically a chip and you are writing its data sheet in code form. Look at this diagram. That green box is the module itself, module my circuit. On the left side, you have got pins going in, input A, input B, input clock. Whereas on the right side, output out, output ready. Just like a real IC where you have got a physical pinout diagram showing which pin does what, a Verilog module has a port list doing the set exact same job, telling the outside world here is how you connect to me. And everything inside that green box, that's the module body, that's where your actual logic lives. Written in whichever abstraction level you are using, behavioral data flow or gate level. Straight from previous lecture. The ports are the interface, the body is the implementation, two different jobs, two different section of the code, and mixing them up is one of the most common early mistake. Let's get specific about what's happening at those pins. Let's port come in three flavors. Input A pin, only the outside world can drive. Your module can only read it, never write to it. Output, the reverse, your internal logic drives this pin and anything outside the module, just read it. And in out a pin that can go either direction, less common, but it exists for things like bidirectional data buses. Now signals, the wires living inside your module connecting your logic together. Two types matter right now. Wire, which is just a plain connection with zero memory. It exists in data flow and gate level code, literally just wire, no storage. And REG, which holds a value in between updates. This is what you will see inside behavior always block. And here is got that trips up literally everyone in this course at some point. REG does not mean this becomes an actual hardware register after synthesis. It just means this signal is assigned inside a procedural block and always block. Whether it becomes a real flip-flop or just plain combinational logic depends entirely on how you write that always block, which is a whole conversation for a future unit. For now, just remember REG is a syntax category, not a hardware promise. Okay, here's the one sentence I want you walking away from this video with, and I want you to actually pause and let it sink in. Order in the code does not equal order of execution. Here is genuinely wild fact that proves it. If you took your Verilog file right now and you literally cut and pasted your always blocks so they appeared in a completely different order, top to bottom, totally rearranged, the simulated hardware behavior would be 100% identical, not similar, not mostly the same, identical, because the position of a block in your text file has zero relationship to when that hardware actually operates. They all live all the time watching their own signal, completely indifferent to where they physically sit in the file. If that doesn't feel a little mind bending coming from a software background, it should, because in C or Python, reordering your code changes everything. In Verilog for concurrent blocks, it changes nothing. So, recap in one brief, hardware is concurrent, not sequential, because that's physically what hardware is, a bunch of independent live circuits, not a to-do list. Verilog modules are structured like a chip dataset, ports as pins, body as internals, and the order you write your always block in doesn't matter or live all at once. Next video, we are tackling something that trips up almost everyone the first time they see it, top-down versus bottom-up design methodology and the difference between a module and module instance, which, spoiler, is basically the difference between a chip datasheet and an actual physical chip soldered onto a board. Same confusion people have with classes and objects, except for hardware. Subscribe straight in the playlist, and I will see you in the next lecture. So, dear students, this is the playlist for Introduction to HDL ED302 related to RGPV syllabus. Thanks for watching.